Hello, everybody. I'd like to welcome you to the CMI webinar series that has been designed for and by the Critical Materials Institute. I'd like to tell you a little bit about the series today and how we're going to kind of conduct business. Of course, these CMI webinars are hosted by Colorado School of Mines. And however, as you know, in this time of COVID, we're broadcasting from all over. So welcome again today, and we look forward to having a very engaging presentation for you. We are always looking for new webinar topics, so we'd like for you to offer up any ideas that you have. Thank you so much, because we do appreciate that, and we'll follow up for you. This is a public webinar, and the recording is going to be available next week at ameslab.gov/CMI. I want to remind you now that this venue is under Workforce, so look under the Workforce tab for any past recordings. We are going to go straight through the presentation. At the end, we will entertain questions, and I'd love for you, we're going to be doing that through the Q&A box on your laptop. And what we'd like to do is when you have a question, go ahead and put it into the queue, because it does take a while to type. And again, immediately after the presentation, our presenter will be taking questions. I'd like to introduce our presenter today. And we have with us Dr. Perez Garcia, and she's an associate scientist at Ames Laboratory, leading a collaborative project with Federico Zaharev and Benjamin Hay for CMI. She completed her undergraduate chemistry in chemistry at Idaho State University. She also has a PhD in chemistry from Iowa State University with the Teaching and Research Excellence Awards added on to that. Her research interests, which you're going to hear about today, include traditional electronic structure theory and new machine learning computational tools for predicting properties of metal lignin complexes, especially as they pertain to critical materials. And I don't want to take any more of our presenters' time. So Marilu, if you'd like to take it from here.
Yes, thank you for the introduction.
You're welcome.
Yes, I will be talking about our research project on machine learning and using that to determine selectivity for metal ligand complexes. And just stepping back a little bit, the reason this is an important topic in CMI is the emphasis on trying to get pure materials from raw and recycled sources. And that typically involves processing, extraction, purification, and so we're focusing in on the extraction portion, and more specifically on solvent extractions. Solvent extractions, just to give you an overview and we're all on the same page, solvent extractions involve typically a two-phase liquid-liquid system. And so here I have our organic phase, so an organic solvent with ligand dissolved in it, and then an aqueous phase where you have metal ions represented here by the stars and these other figures. And so what happens is initially those two are mixed together, and the ligand ideally pulls out one of the metal ions of interest. And so this process is then the metal ion of interest is removed. And that's how this process is able to separate different metal ions. And this process can be repeated several times, and usually is, in order to get a concentration of the metal ion that you want. Of course, a more realistic system, there's usually far more metal ions in the aqueous phase, and the ligand is not nearly as selective as you might want, so you pull out more ions than than just a single ion may be of interest. So assuming that the blue star represents the metal ion of interest, you see that you get a mixture of things. And so again, this process is repeated. Your ligand is often recycled, and there's a lot of different properties of this system that can be studied. You can study the organic phase, the aqueous phase, the interactions between the ligand and the metal ion, the interactions between the ligand and the solvent. And in fact, we did some of that work as well. We studied the organic phase, and using a simple model and continuum solvent models to try to correlate the and try to understand which organic solvents are best for different systems, different ligands. And this takes a lot of work. So to try to focus in on the various aspects of the system takes a lot of work. It's very time consuming. And in fact, for understanding the best organic solvent, we don't have a lot of data, experimental data to compare to. So it's limited into to determine whether we're on the right track. So instead, the reason we're focusing on selectivity and the binding is because it's a simpler, well, maybe not simple, but it's an important factor that gives us an ability to hopefully get more selectivity and more of the ion of interest in the organic phase. So fewer cycles have to be repeated. And also there's less waste during that process. So our goal is to use machine learning to do that. And I'm going to talk a little bit about what the algorithms are learning about, and also how we are creating a database that allows for us to use data to determine selectivity. And the beauty of machine learning is that you can keep improving the algorithms as you get more experimental data and more data from chemical models. So how do we predict selectivity? Well, selectivity is related to, or is defined by comparing stability constants between two different metal ions with the same ligand. And so here I show the definition of a stability constant. And so I represent my metal ion here with a hydrated metal ion, the ligand, and then the metal ligand complex. K is just the concentration of the metal ion complex relative to the concentration of free ligand and free metal ion in water. So we're focusing on stability constants in water. Comparing two different Ks is what gives you the selectivity. So we need to be able to predict the stability constants for different metals, for different ligands, all on the same scale. And we think that we have that this is possible based on a lot of research that has been done previously. There's been a lot of structure activity relationship studies done. Here I have an example from 1976 where there is an equation was developed that showed that if you have, for example, one functional group, one amine, you can have the value for that. And then the more amines on a particular ligand can be used as part of this equation to get the log K of that ligand, that polyamine ligand. And but I do want to point out that these are all on separate graphs because, so these are the linear relationship between observed and calculated with this method. And these are for different metals. They're all on different graphs because this equation is dependent on an empirical value related to the metal ion. So there's a different equation essentially for each of these, each systems. And if we want to predict, we want to have them all on the same scale. But this is promising in the sense that we know that there is a relationship between the structure of a ligand and its stability constant. newer, more complicated equations have also been developed, and these encompass more ligands. But again, the values are dependent on the metal ion and also on the different ligand features. So we're not on the same scale. These are all empirical equations that do pretty well in giving you a good relationship between experimental and predicted. So this again is more promising data that shows that perhaps there's something we can do with greater amounts of data. And so there's also the ability to take information from quantum chemistry. So in CMI as well, so there's a study of uranil, which is a UO2 complex, and using computational methods, they were able to show that you can get a good correlation with experimental and calculated values, but you do have to do some corrections in order to get that really good fit and low absolute errors. If you just do the calculations, the actual absolute errors can be quite high. So once the correction, you do get very good linear relationships. But again, this is for a single metal ion or a single system. And but it shows that there are properties that can be computed that can give linear relationships. We also did a study with a different metal ion. So this is just kind of belaboring the point that you need different equations, different methods to get these relationships when you have different metal ions or different set of ligands. And in this study that takes several months to do all the calculations and all the comparisons and get the proper setup, we show that you need to include the solvent in the optimizations so that you get good structures for computing this linear relationship between computed and experimental. So all of that to say is, can we combine those computed and empirical data to get selectivity in a single method? And that's where we move towards machine learning and AI. Dr. Federico Zahariev is our group expert on machine learning. And while machine learning is a hot topic at the moment, it's actually, the idea behind it has been around for a long time. It is basically trying to mimic biological learning, but through computer code and programs. And now with deep learning, it's much more computer science, mathematical. Well, I guess it was back then too, but there's with newer compute resources, you can do much more sophisticated programs to do the learning. And so just a note, AI is an umbrella term, and machine learning and deep learning fall under that umbrella. We typically use the term machine learning. We use neural nets to do the comparisons between experimental and computed. And we also incorporate some data mining in our research because data is needed, and sometimes data mining also uses AI to mine for data. But so a kind of simple example of how to use machine learning to get some correlations is, if you have a data set, you can teach your algorithm based on giving it images, in this case, to match up to a particular digit. And the way that the machine learning works for this type of character recognition is it takes the image and it breaks it down into a matrix of numbers. So these squares represent dark or light colored square by a number. And once all those numbers are fed into your algorithm, it can match up the nuances, the different characteristics of an image that enable it to understand that it's for example here, a 2. And so how does that relate to, well, first, the point I want to make here is that you need numerical data and you need a lot of data. The more data you have, the more or the greater ability of your algorithm to understand the various nuances to get the right values. And so we have that data. It took a while to get the data in a format that we can use. We worked in parallel to get to try and find the most appropriate way to get data. So stability constant data has been compiled for many years, decades, starting from the compilation of physical books by Smith and Martel. And then NIST was also interested in compiling them into a digital database. And we did OCR work to try to pull data out from the books. We worked on trying to pull data from the digital database into a format we can use. And all of these things we were doing in parallel because we knew that our research hinged on having numerical data that we can use to teach our algorithm. Luckily, we were able to do that in the winning way was through Dr. Federico Zahariev pulling some of the source code of some of the databases that we were able to get our hands on. And as you see, there's a lot of data for various metal ions, for various ligands, and out of the 25,000 or so data points, about 6,000 are under the same conditions. And so they're the ones that we are focusing on for this research. As far as the ligand goes, you have to represent it somehow. So the idea of doing it as an image is not really feasible. Just thinking about a simple acetic acid molecule in this figure, a chemist would immediately realize that this is a carbon with 3 hydrogens. Here is another carbon that's bound to 2 oxygens. And so as an image, we have a lot of information here, but a computer doesn't recognize that. And if we do an image, there's a lot of pieces that are missing and it's not interpreting. Also, you can do different images. And so the idea of using an image is not going to work. And so luckily, there are a lot of databases to kind of transfer between a 3-dimensional structure into a name. There are registry numbers to get unique identifiers for each ligand or for different ligands. There's also a lot of tools that were developed for chemical informatics that we can also use for this research, including RDKit, which is very powerful. It can convert from 3-dimensional coordinates to a SMILE string, and that's actually what our code does. So just to give you an overview of what a SMILE string is, it's basically a set of directions to break down a complex molecule into a single string of characters. And so, for example, here you see where all the cycles are broken, and then you can create a chain that is, or you can designate a chain and then the branches off of that chain, and then represent it as a string of characters. And within the string of characters, you have all the bond connectivity, all the atoms, the rings. And so this is not super visually friendly for a human, but it's more, it's better equipped to be used in a computer program. And we're still not at a numerical value for a ligand. And so that is done by converting. Here I have the simple acetic acid again, convert it to a SMILES, and then the code, which this is some methods that have been developed by other groups, is to convert the molecule into a directed acyclic graph. So it breaks all of the cycles as well. Each atom is represented by a node, and then there's arrows that point. All the arrows eventually point to a single atom. And so this is directed acyclic graphs, or DAGs, is an area of computer science and math that allows you to deal with this type of system is in a numerical way. But you might be thinking here, well, if all of your arrows point to a single atom, you might intuit that you are biasing this molecule to have some sort of importance on a single atom. So what is actually done is an averaging of the molecule where in each DAG you have a different atom of emphasis. And so by averaging all these out, you get you're able to get a non-biased way of looking at the molecule. Okay, so all of those pieces together, how does it relate to this idea of machine learning? Well, we don't have an image to break down into numerical values, but we do have a bunch of numerical values. And we can describe the system in the ligand with a DAG. We can include the metal as part of the SMILE string. We can also include other computed or other values in the database that represent the system. And then using a known set of systems with known values of log K, we can do the similar thing where you train your algorithm to pick out the different nuances from the various combination of properties and assign them the proper log K. And these properties that I'm showing here are not necessarily all of the ones we want to use or a exhaustive list or even necessarily the list that is going to give us the best results. So far, what we've done is we've looked only at the DAG. And so we've just correlated the DAG with the, or trained the algorithm with the DAG and the log Ks, the experimental log Ks. And we already see that there is a pretty good linear relationship. We did several trials. This is for the 6,000 log K points that I said we would focus on because they have similar experimental conditions. And you get pretty good results. In order to improve off of these results, we want to be able to add some of those other properties. So that limits how many points we can actually use, since we have to do, we have to compute some of those values, and that can take some time. So we can also, by doing these little, or by doing these trials, we can also pick out and try to understand what the algorithm is doing and maybe what it's missing. So for example, I'm highlighting here these points where there was a high error, and they correspond to this ligand here. And if you recall from the beginning of the talk, I mentioned that there are ways of doing an empirical equation that relates the number of amines to a single amine. So if you have a ligand with multiple amines, it's some sort of additive equation. And it seems that the algorithm is kind of picking up on that idea as well. In this case, you have 6 amines. And so if you naively just look at the fact that there are 6 amines, you might think each one has an additive effect to the log K, and so your log K should be really high. But of course, we know that there are longer distance relationships about the ligand that may mean that it cannot bind all nitrogens to a metal ion at the same time. And so there are some competing factors, some longer range factors that don't allow for the log K to get that high. So it's interesting to see that this is the type of mistake that it makes. And so we're kind of continuing to do that, and that hopefully will also guide us into what properties to include that might help improve the correlation. This is just to say that we have a subset of data. So this is for 6,000. This is a subset of data where we plan to do these computations with molecular mechanics and quantum mechanics, and also find data from the literature if it's available to include. And so these are the numbers we're trying to improve on. This is the subset of data that we're trying to improve. part of the research requires us to also do some method development. And I want to highlight the work of Dr. Ben Hay, who has expanded a molecular mechanics model in order to be able to construct structures that include a metal ion. Typically, molecular mechanics models don't do a great job of creating structures with a metal ion in them. And with using a crystal structure database, he was able to generate the parameters for 46 different metal ions, and comparing with over 17,000 structures, he gets very good agreement, very low bond distance errors, bond angle errors, and torsion angle errors. And here, these images are different types of, this is just a small subset of different types of ligands that there are parameters for. And the color and the black structures are the crystal structure versus the molecular mechanics structure. And as you can see, they overlap very well. And so that's part of where we're getting some of our data. So far, I haven't really touched much on the computer-aided design portion. I've mainly talked about the machine learning aspect, but the design piece of the ligands comes from host designer. Also, Dr. Ben Hay designed this code, and it's freely available already. And it's one word on SourceForge, host designer, one word. And what it does is it contains a library of molecular fragments that it combines to form a larger ligand. And then it can rank these for a single metal ion to rank which are the best for a particular, the highest binding for a particular ligand, a particular metal, and different ligands. The great advantage of this code is that it can build and evaluate millions of molecules in minutes. It gets 3D molecular structures, and it already has all these pre-computed molecular fragments. And as I mentioned, the MM3 force field parameters has been expanded to, so aside from actually computer design, you can also do, can get structures for organometallic compounds. And so the idea being that from a large set of molecular fragments, you can start weeding out the types of molecules that you would not expect to do well, and start getting a refined list of candidates. The reason this doesn't solve our problem of selectivity is that it does one metal at a time. And that is essentially what we are moving towards with this research, is combining that ligand design code so that you can rank based on selectivity that is gotten from the machine learning output. And so a lot of the current work that is being done right now is interfacing, adding the additional data. And because the beauty of machine learning, you can add more data and start to improve your correlations. We are also always looking for collaborators and people who can do, who can provide data, experimental data, and of course, from chemical models as well. So that's all I have for you today. I want to thank our funding sources, and also we've had many conversations and a lot of good suggestions coming out of the Windus group, Gordon's group, and Focus Area 1, which is our main, which is where our project is in relation to CMI. This is my contact information. And thank you all for your kind attention. So I think we have time to do questions.
Marilu, hi. I wanted to thank you very much from CMI for your great presentation. And what another way to look at analyzing data and that can give us additional ideas for more research. Again, when you talked about the selectivity, to also make it more refined so that we're also thinking about things that can give us more output into the future. And wow, I think it's just amazing. You know, when you look at something like this, it's almost like better data gives you better analysis. And so thank you again for adding this so that people in our world in CMI can even think further about how they would use your group to help them solve some of their current problems and investigations and go further with it. So, and help refine them actually. So great presentation. We are opening up for question and answer right now. And I would like to just ask Marilu, as we're waiting for questions, if by chance you had any concluding comments or ideas of where else you'd like to take this research that you might share with CMI.
Thank you for that question, Cynthia. Yes, we have some ideas of where we want to move to. One of the things that we've bounced around and that is also part of Host Designer is synthetic accessibility. So the ability, how easy, if we can rank the ligands on how easy they are to synthesize. And so that's something we're continually looking at for the future, because the ligands, of course, need to be accessible and easy to produce in order to make it a viable option for industry. But there are a lot of things. This system is very rich in questions that you can ask. We've already looked a little bit at the organic phase and what different aspects of that can give us. There's also whether the aqueous phase is acidic or what kind of counter ions there are. An important question is what the interface between the organic and the aqueous phase look like. So there are a lot of questions. It's a very rich system, and we're focusing on the binding site because there's a lot of data already out there, and it's also a very important part of what makes a good ligand.
Marilu, thank you for that information. And we have 3 more questions here lined up for you.
Yeah, so we have a question from Jeff Boshin. So thank you. It says, how do you represent cyclic molecules using a DAG? So yes, a directed acyclic graph implies, there's no cycles within it. And you can do a couple of things. You can either break down, you can collapse the cyclic parts of a molecule into a single node. Unfortunately, this does decrease the accuracy in older or in previous studies. This decreases the accuracy of your algorithm. And so instead, there is somewhat of a programmatic way of cutting the cycles so that it's consistent among all of the cycles, or as consistent as you can. And since the log Ks are dependent on teaching the algorithm, you can still get that information via a directed acyclic graph. So thank you. All right, so the next question is from Raul Miranda, and he asks, if one wanted to be cognizant of the F element character of rare earth elements, are there enough experimental data and quantitative methods with relativistic corrections data to use machine learning to fine-tune ligands for extraction? If so, which are those databases? It's true, the databases have fewer data for F elements. I guess in that case, we do want to look at the computational properties that we can compute for those. But it's something we have to look into. As far as which databases, so we have a combination. Actually, I didn't really mention this. There's 2 databases. There's the NIST database and the IUPAC database that also has a large amount of data. So if you're interested in those particular databases, please reach out to me and we can see how we can share. I think you can also get them directly from IUPAC. So it has a little bit more data, but it is an issue. And so we're always looking at how to improve. It'll be clear, I think, once we start digging into the results of the individual systems, trying to look at different atoms. But so far, I don't probably have the best answer for that. The next question is from David Reed. Can any ligand identified be synthesized? How complex can the ligand be? Yeah, so it's the design element is limited by what host designer can do at the moment. Of course, you could always create a list of ligands and we could run it through and see what the predicted log Ks would be for different metal ions. So there's a couple ways of dealing with that type of situation. But from the design aspect, a clearer answer would come from Ben Hay, since he developed the code. But so far you can do definitely a bidentate with different types of just almost anything as far as a linker. And so the molecules can be quite complex, and so that there are ways of actually reducing the complexity so that you can get a list of ranked ligands that don't have some of the harder to synthesize linkers. Yeah. Thank you for your questions. Last, I think, question is from Lionel Toba. Are you using an already developed machine learning algorithm, or are you starting from scratch, and how do you improve the algorithm? So we are not using one from scratch. It is ChemProp, I believe, is the one that we've been testing out. We started off by testing a lot of different ones, and we're also kind of looking and seeing if we can do a little bit of studies on the side that with original code that Federico is developing. But what I showed so far is with ChemProp, but it wasn't designed to do what we want to do. So we're using it for a new application. And the way we're improving it is by including more data. And so that's a lot of where I come in, is doing the calculations and trying to do a large amount of data, acquire a large amount of data using quantum chemistry to include, and that's basically what we're doing to try to improve the results. So.
We do have a little bit more time for another question, but what I will do at this point in time, while we are waiting for a question, I'd also like to thank Marilu again for a great presentation. And again, this just really opens up a lot of possibilities for CMIers doing research to gain greater analytical abilities. And we do have one question that just came up again. If you want to answer that before I do the final thank yous.
Sure. So another question from Lionel, and he's asking, are you not worried about overfitting with large size of data? That's always a concern. So we just use the same procedures that is typical for machine learning, and how you validate your algorithm. So you use different methods of what you use to train, and be careful with that and not over represent the same type of data, and then your validation methods. I'm not a machine learning expert, so that's the best I can do, but I'm happy to connect you with Federico and he can give you more information, but that's my understanding.
Okay, Marilu, again, thank you. Thank you for being the last webinar of 2020. I want to thank the audience here for being engaged with us during this time. I want to wish all of you a very special holiday break we're all looking forward to. We're going to see you in the new year, and we're working on the next webinar will be advertised in the critical times. We also, again, want to remind you that this recording is going to be available next week at ameslab.gov/CMI, again, under the workforce menu. If you have any additional topics, we'd love to hear from you. We look forward to seeing you in the new year. Thanks again.
Thank you.